Hello everybody and welcome to the NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 14 and we will carry forward our understanding of second order effect, and we will be concentrating more on channel length modulation effects referred to as CLM and subthreshold conduction. So, the outline of this presentation will be, we will look into CLM, the channel length modulation effect, how the current versus voltage relationship is available when you include channel length modulation effect, how does transconductance vary if you take CLM into consideration, small signal model. We have already seen the effect of bulk potential on the threshold voltage in a previous lecture. Here we will be looking at the effect of bulk potential with CLM on the current relationship. The second part of the lecture will be on subthreshold conduction. We will looking into the MOS subthreshold characteristics, and then finally end up with advantages and disadvantages of operating MOSFETs in subthreshold region. So, let me start with channel length modulation effect and see what is channel length modulation effect. Now, if you remember correctly that if you apply a drain bias in any MOSFET, because of a strong electric field, the electrons start moving towards a drain and the conventional current is from drain to source and the source is grounded. So, I am assuming now that two things is happening. So, let me say my gate voltage VGS is much larger than threshold voltage of the device, which means that inversion is actually being formed. This is basically N plus. So, this is basically you have a P type substrate, and because of P type substrate, inversion layer has been formed. If you did not give any drain bias, then the inversion layer will look like is something like this, and then you have the metal layer, and then you have metal contact here, and then this goes to the metal contact, and then you go to the gate to source voltage. This is N plus N plus. Now, this is where you apply a drain bias and the source is grounded, right. We have been doing this for quite a long time. With this phenomena, if you did not apply any drain bias, obviously the depletion thickness will be something like this, right. So, there will be equivalent depletion thickness both on the source side and drain side. But what happens, let us see, if you go on increasing the drain value of the drain bias. As you go on increasing the value of the drain bias, this depletion thickness on the drain side, it goes on increasing because it is a reverse bias PN junction diode. As it goes on increasing, it will some point of time start eating away into the inversion layer which is available at this particular point, which therefore means that as you move from source to drain, your depletion thickness becomes larger and larger, and that is what is shown on the left hand side figure here. You see, because of this, the depletion region has actually entered into the drain region, and then this goes like this, which means that as you move from source to drain, your inversion layer is getting tapered off, right, and it is getting tapered as you move from source to drain, and that is what is shown here. Another way of looking at it is that let us suppose you apply a drain bias of plus 1 volt, right. Then what will happen is this will be 0 and this will be 1 volt, right. Somewhere in the middle it will be 0.5, middle of this will be approximately 0.75, middle of this will be 0.25. Please understand, this is positive gate voltage here, and this is positive, and this is P type substrate, right. So, you are effectively giving a bias, and let us say my gate voltage is say 2 volts, assuming it to be. Then the difference between this and 0.75 is just 1.25, whereas the difference between 2 and 0.25 is 1.75. Therefore, which effectively means the electric field here in this direction will be stronger and here it will be weaker. And that is also visible from the fact that you now have a larger amount of inversion charge near the source end and you have lesser amount of inversion charge on the drain end. If you still go on increasing the value of drain to source voltage, the point where you are getting a pinch off here, this is known as pinch off point, where the inversion layer finishes, will start shifting to the left towards the source end, because depletion thickness becomes more and more, which means therefore that, and that is shown in the second graph, that this is what is happening, that there is a reduction. When there is a reduction, your effective channel length is getting lowered by a factor of delta L, let us suppose. So, this was your L, this was your L, and this is delta L. So, the effective channel length is L minus delta L, fine, and therefore, this is known as channel length modulation, that with increasing drain to source voltage, if the effective channel length starts to reduce, then we define that to be as the channel length modulation phenomena. right. Let us see how the equations are there. We already know that in saturation the drain current equation of a bulk MOSFET is given by 1 by 2 mu n C oxide W by L. L prime, let us we have replaced L by L prime, where L is the original length and L prime is the shortened length, effective length after you have applied a CLM. So, it is W by L prime into VGS minus VTH, and therefore, my delta L is original minus the reduced one, which is L minus delta L, implies that my delta L will be L minus delta L, which is very true also. So, this will be equals to L minus delta L, and I am assuming that my L is very large as compared to delta L. That is what is there, right. And therefore, if you do small manipulation, I get 1 by L prime approximately equals to 1 plus delta L by L divided by L, taking only the first order expansion here. Now, delta L by L is equal to lambda times VDS. Lambda is known as the CLM parameter, right, and well, yeah, this is the CLM parameter or CLM coefficient. Then what happens is, if you take this expression or even if you take this expression and fit it at this particular point, I get current equals to 1 by 2 mu n C oxide W by L, VGS minus VTH whole square, perfectly fine, no problem. I get 1 plus lambda VDS as an extra term. If you expand this term, if you multiply this with this, the first term will be, so if I remain this, if the first term will be 1 multiplied by this, which is exactly what I get. So, the first term will be ID will be equals to 1 by 2 mu n C oxide, right, W by L into VGS minus VTH whole square. This is the first term, and then the plus, you will have 1 by 2 mu n C oxide W by L VGS minus VTH whole square into what? Into you will get lambda times VDS. So, this factor tries to increase the value of the total drain current. Now, you see, if my delta L by L is large, it implies my CLM parameter or CLM coefficient is also large, means lambda is large. Lambda large implies that my ID is a strong function of VDS. If my lambda is small, it implies that my ID is a small function of VDS. Lambda large implies delta L by L is large, lambda is small implies delta L by L is small. So, if my lambda is relative, say it is 0.001, it effectively means that delta L by L is approximately equal to 0.001. Whereas, if I make it delta L by L is equals to 0.1 only, then there is a 10 to the power 3 order change in the value of lambda, and therefore, CLM will be more prominent if you have a higher lambda value, correct. So, this is your final CLM equation. It depends upon the overdrive. VGS minus VTH is also referred to as overdrive, right, and it depends upon 1 plus lambda VDS. Just keep this in mind as far as your current versus relationship is concerned. This is where we now come into the picture. Now, let us assume that you did not have any CLM. If there was no CLM, this component will be 0 or will not be present actually. It will be, so, lambda VDS will be equals to 0, and therefore, the only term present will be 1 by 2 mu n C oxide W by L VGS minus VTH whole square. This is in saturation. It is not available in the linear region. That I will explain to you why. In saturation, therefore, your VDS is relatively high, which means that your VDS is greater than equals to VGS minus VTH. It is relatively high. If it is high, then let us see its implication on the current expression. Look at the diagram shown here on the below. Now, if you look at the diagram here, then current and versus VDS is plotted. If there would not have been any challenge in modulation effect, then this is without CLM, and that is true also. You see, if you look at just this expression, only this expression only, then there is no function of VDS. Therefore, ID therefore is not function of VDS. However, when you have a CLM, ID becomes a function of VDS, and therefore, for a fixed value of lambda, let us suppose it is 0.1, then VDS if you apply as 1 volt. So, this will be 1 into 0.1, an extra 0.1 will come into picture. When you make VDS equals to 2, an extra 0.2 will come into picture. So, initially this favor will be 1.1, then 1.2, 1.3 and so on and so forth, and that is the reason you see a rising current here, fine. First thing. The second thing is, as you make the VGS value larger, since your overdrive becomes large, your effective current also increases. So, you see the separation here and the separation here for the same value of VDS is larger for VGS2, and I say that VGS2 is larger than VGS1 because it's a square term is coming into picture. So if it would have been linear, the increment would be same, but since it's a parabolic term, the increment is higher for a higher value of VGS. So two things we get out of it. One is, first of all, without CLM, my current is constant independent of VGS. With CLM, the current is a function of VDS and it goes on increasing as the value of VDS goes on increasing, and therefore there is a slope. Let's look at its implication. The implication here is that if, since it's perfectly a straight line, if I want to find out the resistance of the device, it is del V by del I in dynamic resistance. Del V is okay, some del V I am giving, but my del I is 0. So my R happens to be infinity, and it behaves like almost like a ideal current source whose output impedance is infinitely high. Whereas if you have CLM, then R will be del V del I, and for this del V, let us suppose I get this much amount of del I. This is my del I, right? And therefore resistance will have some finite value. Agreed that as you go to a lower value of VGS, your del V del I will be larger and the resistance will be larger. So higher the value of gate to source voltage, lower will be the resistance, more sharply the current will rise with respect to VDS. Correct? Okay, so this is channel length modulation effect. Let's look at the fact that if I do ID versus VDS and I just go on increasing the dimension of the device by twice, which means that I increase the channel length by twice. You see? So I had one channel length of L1 and then I have a new channel length of double the L1 value. You see, the effect of CLM is actually reduced. Why? Because now effectively the drain and source are far apart from each other. Not only that, delta L by L value will reduce when you have a larger channel length. When you have a shorter channel length, and if you have a larger channel length, your depletion thickness is this much only, here also this much only. So this divided by this will be much larger as compared to this divided by this, and therefore your lambda will be lower, and therefore you see your value of current is actually falling down for a larger and larger value of VDS. Correct? So this is the effect of doubling the channel length over a period of time, right? So the reverse is true. As you reduce the channel length, therefore CLM is higher and your resistance actually goes down, right? So resistance therefore also is a function of the applied not only gate bias but also the dimension of the channel length. Now let's come to transconductance of the device, right? Transconductance is defined as GM, which is basically del ID del VGS, right? Now let's go back and I will explain to you physically and then maybe I'll explain to you numerically what will happen. Let's look at this slide. Let me rub this portion at least. Now let's just concentrate on a fixed value of VDS, right? Fixed value of VDS, and let's look how does it work out. Let's just concentrate here, right? What I told you GM to be equals to del ID del VGS, gate to source voltage, right? Now for a fixed value of VDS, basically what I'm looking into is I'm looking at this VGS here and this VGS here, and I'm trying to extract the value of GM, transconductance. You will see as you move to lower values of VDS, right, this difference will be, this change in current will be lower, whereas if you go for higher value of VDS, this change in current will be much larger. This change will be much larger, which implies that for a higher value of VDS, del ID del VGS will be larger, whereas lower value of VDS, del ID del VG will be lower, which means that my GM transconductance will be smaller, right, for smaller VDS. This is one thing, correct? If there wouldn't have been any CLM, let's see like that, if there wouldn't have been any CLM, then how should I take the transconductance? This and this divided by these two, which means that GM will be almost independent of VDS when there is no CLM, or my lambda equals to 0, right? So GM now becomes a function of VDS. Let's come back to the expression which I told you. This is how it looks like. GM is mu1 C oxide W by L VGS minus VTH 1 plus lambda VDS, and as you can see, it's function of VDS GM now becomes, which I just now explained to you physically. And this is also another way of writing it, where you have a constant current methodology, by you say that U2 mu1 C oxide W by L ID upon 1 plus lambda VDS. So this is where it basically function of that. This is a constant current model. So that's the reason lambda VDS is in the denominator of the transconductance equation. Now let's come to the small signal model of the device using CLM. Small signal means when you apply a signal such that the variation in the signal is just plus minus 10% of the nominal value, we define that to be as a small signal model, right? And you can easily assume that the devices are linear in this region of operation, right? These are not large signal, small signal models are there. So let's look at the left hand side and then we'll go to right hand side. In the left hand side, you will see this, so there are three terminals. There are three terminals, and the three terminals are gate, drain, and source. So the voltage between gate and source is given as plus this VGS here. Between drain and source, there will be a current flowing, which will be defined as GM times VGS. Why? Because GM is equals to del ID del VGS, right? So if you cross multiply this, I get del ID to be equals to GM times del VGS, correct? If you remove the del from both the sides, I can safely write down this to be as ID equals to GM times VDS, and you can see the direction of current is shown here. This is without CLM. Let's come to with CLM. With CLM, what happens? You have a current which is a function of VGS for sure, this one, which has to be there because it's a FET device. But you also have a current now which depends upon alpha times VDS. It is a drain dependent current which is flowing, and it is supporting my primary current. It is helping my primary current, and that's the direction of the current sources are exactly the same in both the cases. So I have two components with CLM. One is with GM times VGS here, and we have another one which is alpha times VDS. You can take alpha any value here, or in fact lambda times VDS is also a good idea to take into consideration, where lambda is basically the channel length modulation parameter, which is, in fact this should be lambda times VDS, right? So this is the small signal model including the channel length modulation effect. Now if I say therefore the current source whose value will linearly depend upon the voltage, you see there is a linear dependence on alpha VDS. If you go back here, you see GM is a function of lambda VDS, a linear dependency is there, right? So what I was talking about, that in linear resistance in presence of CLM, if there would have been an absence of CLM, I told you the resistance will be infinitely large. Because of the presence of CLM, there will be a resistance, equivalent resistance, linear resistance available in the output of the current source. And this resistance is given by what? Del VDS del ID, right? Del VDS del ID, and this is nothing but 1 by del VDS del ID, and this is given by this quantity, right? If you differentiate ID with respect to VDS with CLM parameter, you get this into consideration, and this is nothing but my ID equation, original ID equation. So I get 1 upon lambda ID, which means that interestingly I can replace therefore the current source, this current source, by a simple resistor. Ideally, if you remember, the current source has got a output impedance is infinitely large, right? But since now I have a finite resistance for the current source because of the CLM effect, I automatically get a resistance here R0 available to me, which is in parallel to the channel current source. So I have a current source in the channel because of the inversion layer, and there will be a resistance between the source and drain known as channel resistance, and that will be equivalent to 1 by lambda times ID. So it's 1 upon lambda ID. Interestingly, therefore, this is equals to your R naught. As the lambda value increases, R naught will decrease. As the lambda value increases, R naught will go on decreasing, which is a very perfect way of saying that the resistance will fall down as the lambda value increases. Now let's take two effects together now. We have already studied the bulk potential effect and the CLM effect together. Now if you remember in our previous discussion, we were saying the bulk second order effect. So the bulk or the body behaves as a second gate. You have a top gate and you also have a bottom gate effectively available there, and therefore the current will not only depend upon the top gate, but it will also depend upon the bottom gate. And let us assume that let us define a term known as GMB, which is del ID del VBS, which means that GMB is transconductance, bulk transconductance, and is given by the rate of change of drain current with respect to bulk to source voltage, and this is shown as GMB here. So you have GM is the transconductance of the channel because of the gate voltage change, the current change in the channel, and this one is the current change in the channel because of the source voltage. Now I will not go into details of how these are derived here, but we already know that GMB can be expressed as del ID del VBS, right? This is the expression is. If you solve it, you get this into consideration. A new term comes here, and that is del VT del VSB, right? Why? Because now, if you remember earlier, if you didn't consider the variation of threshold voltage with bulk voltage, this quantity would have been 0. My GMB should be 0 if del H del VBS is equals to 0, right? So if there is no body effect, obviously my GMB will be also 0, and which implies that there will be no change in the current even if you change the bulk body bias. Also, we know that del VTH del V is given by this expression, right? So what you do, you just plug it in here, and you can get the new value of GMB from this particular point, where we know that V is equal to V0 plus gamma times the factor which we have already done, right? So this gives me expression of how threshold voltage is changing with bulk to source voltage, and this is where we come to GMB. So GMB therefore becomes equals to GM times gamma by some factor here, and it is given by eta. This factor is defined as eta, and I get therefore GMB by GM equals to eta, where eta is given by gamma lambda upon 2 plus, so this is lambda upon 2 into root 2 phi f. So now my GMB by GM is both a function of the CLM parameter lambda and SB, the backgate bias. If you take this into consideration, let's see what happens is the new small signal model of MOSFET with CLM and body effect. This is your primary current which is flowing, I discussed with you. This is the resistance which is available because of the CLM parameter, and we get a third term which is GMB times VBS as a current source because of the substrate bias which is given here. Bulk is positively charged with respect to source. So the total current will change if you take both CLM and body effect into consideration, right? That's what is shown in this example. And GMB by GM will have a function of eta, where eta depends upon the value of lambda, CLM parameter and VSB. So which means that if my lambda goes on increasing, right, I would expect to see my GMB by GM going on increasing, right, and vice versa. And we will recapitulate what we did today. We had understood therefore VSB sub-bulk, and then we came into CLM. The physics behind the CLM from device point of view was explained to you, and how does it influence the small signal model, that has also been explained to you, and we take this and bulk potential variation also into consideration. So with this we have been able to finish the effect of both CLM and bulk potential on a small scale device, right? This is a second order effect which we will be doing. In the next turn, we will take care of the subthreshold conduction, and then we will take all the three together and see what will be the equivalent small signal circuit model, right? So we'll finish here. I hope you enjoyed the lecture. Thanks a lot.